Today we're going to explore the fascinating world of spinning magnetic microparticles and how their behavior changes dramatically across different length scales, from nanometers to millimeters. To understand the physics of spinning particles in fluids, we first need to understand the Reynolds number. This dimensionless number tells us whether inertial forces or viscous forces dominate fluid motion. The Reynolds number equals density times velocity times characteristic length, divided by dynamic viscosity. Alternatively, we can write it as ρHO versus L over mu. Physically, the Reynolds number represents the ratio of inertial forces to viscous forces. When Reynolds is high, inertia dominates. When Reynolds is low, viscosity dominates. For microparticles spinning in fluids, we're almost always in the low Reynolds number regime, where Reynolds is much less than 1. This means viscous forces completely dominate over inertia. Let's pause and ask ourselves a question. Why does the size of the particle matter so much for the Reynolds number? The answer is that Reynolds number scales linearly with the characteristic length. A particle 10 times smaller has a Reynolds number 10 times smaller, assuming the same velocity and fluid properties. Here we see particles at different scales, from nanometer scale on the left, to micrometer scale in the middle, to millimeter scale on the right. Each increase in size affects the Reynolds number proportionally. Let's do a back-of-the-envelope calculation for a typical spinning magnetic microparticle. Let's consider a microparticle with diameter 10 micrometers, spinning at 10 Hz in water. The diameter is 10 micrometers, which equals 10 to the negative 5 meters. The frequency is 10 Hz. The angular velocity omega equals 2 pi f, which is about 62.8 radians per second. The velocity at the particle edge equals omega times radius. That's 62.8 times 5 times 10 to the negative 6, which gives us 3.14 times 10 to the negative 4 meters per second. For water, the density is 1,000 kilograms per cubic meter, and the dynamic viscosity is 10 to the negative 3 Pascal seconds. Plugging everything in, Reynolds equals 1,000 times 3.14 times 10 to the negative 4 times 10 to the negative 5 divided by 10 to the negative 3. This gives us 3.14 times 10 to the negative 6. So the Reynolds number is approximately 3 times 10 to the negative 6, which is much less than 1. This means viscosity completely dominates the physics. There's essentially no inertia. Now let's explore how changing the spinning frequency affects the Reynolds number and the particle behavior. Since velocity is proportional to omega, and omega is proportional to frequency, the Reynolds number is directly proportional to spinning frequency. At 1 Hz, Reynolds is about 10 to the negative 7. At 10 Hz, it's 10 to the negative 6. At 100 Hz, it reaches 10 to the negative 5. Still firmly in the low Reynolds regime. Now let's consider how changing the fluid viscosity affects the system. Remember, Reynolds number is inversely proportional to viscosity. Reynolds is inversely proportional to mu. Higher viscosity means lower Reynolds number and stronger viscous damping. In water, the viscosity is about 1 millipascal second. This is our baseline. In glycerol, the viscosity is about 1,000 millipascal seconds, which is 1,000 times more viscous than water. In oil, viscosity ranges from 50 to 100 millipascal seconds, so 50 to 100 times more viscous than water. In glycerol, the Reynolds number would be the water value divided by 1,000, giving approximately 3 times 10 to the negative 9. Viscosity dominates even more strongly. Now let's discuss something crucial. When you have multiple spinning particles, they interact through the fluid. These are called hydrodynamic interactions. Each spinning particle acts like a tiny stir, creating a velocity field in the surrounding fluid that extends outward. For a rotating sphere in low Reynolds number flow, the velocity field decays as 1 over r squared, where r is the distance from the particle. Here we see 2 spinning particles. Each creates a flow field, shown by blue arrows. These flow fields overlap and cause the particles to interact, even without direct contact. The strength of hydrodynamic interaction depends strongly on how far apart the particles are. Closer particles interact more strongly. Let's ask another question. What happens when we increase the concentration of spinning particles? Do the interactions become more important? The answer is yes. At high concentrations, collective effects emerge. The particles can't be treated independently anymore. They form a many-body system with complex dynamics. This brings us to one of the most fascinating phenomena, the formation of dynamic colloidal crystals from spinning magnetic particles. At the right combination of spinning frequency, viscosity, and particle concentration, the particles spontaneously self-organize into ordered crystalline structures. But these aren't static crystals. Every particle is constantly spinning. Energy is continuously being pumped in by the magnetic field. These are dissipative structures maintained by energy input. Here's a simplified view of a dynamic colloidal crystal. Particles arranged in hexagonal order, each spinning continuously. The green arrows show rotation direction. Why do these crystals form? It's all about a balance between several competing effects. First, magnetic dipole interactions cause particles to attract and tend to form chains aligned with the magnetic field. Second, the spinning creates hydrodynamic flows that generate an effective repulsion, pushing particles apart when they get too close. Third, viscous drag dissipates energy and helps stabilize particle positions by damping out fluctuations. There's an optimal spinning frequency where these three effects balance perfectly, leading to stable crystal formation. We can map out a phase diagram showing when crystals form as a function of spinning frequency and fluid viscosity. This simplified phase diagram shows different regions. The green region is where stable crystals form. Red is disordered fluid. Blue shows chain formation. Orange shows clustering. The boundaries depend on particle size and concentration. Let's do another back-of-the-envelope calculation to estimate the critical frequency for crystal formation. The crystal forms when the hydrodynamic repulsion from spinning balances the magnetic dipole attraction. The hydrodynamic force scales as mu omega d squared, where mu is viscosity, omega is angular velocity, and d is particle diameter. The magnetic force scales as mu 0 m squared over d to the fourth, where mu 0 is the permeability of free space and m is the magnetic moment. Setting these equal and solving for omega critical, we get omega critical scales as mu 0 m squared over mu d to the sixth. Notice the strong dependence on particle size. For a 10 micrometer particle with magnetic moment 10 to the negative 15 ampere meter squared in water with viscosity 1 millipascal second, we estimate omega critical as around 10 to 100 radians per second, which corresponds to frequencies of 2 to 15 Hz. This matches experimental observations. Now let's talk about how we can melt these dynamic crystals by changing parameters. This is reversible. Method 1. Increase the spinning frequency. If you spin too fast, the hydrodynamic repulsion becomes too strong and the crystal melts into a disordered fluid. Method 2. Decrease the frequency. If you spin too slowly, magnetic attraction dominates and particles collapse into chains or clusters instead of crystals. Method 3. Change the viscosity. Adding or removing glycerol shifts the balance of forces and can melt the crystal. Method 4. Dilute or concentrate the suspension. Too dilute and particles don't interact enough. Too concentrated and you get jamming. Here's a schematic showing crystal melting. Start with a crystal at 10 Hz. Increase frequency to 50 Hz and it melts to disorder. Decrease to 1 Hz and it forms chains. It's fully reversible. Now let's zoom out and think about how this physics changes as we go from nanometer to millimeter scales. At the nanoscale, around 100 nanometers, Brownian motion becomes very important. Thermal fluctuations can disrupt the structure. You need very high frequencies to overcome thermal noise. The thermal energy equals Boltzmann constant times temperature, which is about 4 times 10 to the negative 21 joules at room temperature. At the microscale, around 10 micrometers, we're in the sweet spot. Brownian motion is weak enough to ignore, but particles are small enough to have low Reynolds numbers. This is where crystals form most easily. At the millimeter scale, gravity becomes important. Particles sediment faster. You need higher viscosity fluids or density matching to keep them suspended. Reynolds numbers also start creeping up. The sedimentation velocity equals 2r squared g delta rho over 9 mu, where delta rho is the density difference. This scales as r squared, so millimeter particles sediment 10,000 times faster than 10 micrometer particles. Let me give you an analogy to tie this all together. Think of these spinning particles like dancers on a dance floor. At the nanoscale, it's like dancing in a bouncy castle, where the floor is constantly shaking. The dancers are being jostled by thermal fluctuations. Hard to maintain formation. At the microscale, it's like dancing on a perfectly smooth floor. The dancers can coordinate their movements precisely. This is where beautiful patterns emerge. At the millimeter scale, it's like dancing in molasses while slowly sinking. The fluid is thick and gravity is pulling you down. Much harder to maintain coordination. These spinning magnetic particle systems aren't just scientifically interesting. They have real practical applications. Spinning magnetic particles can be used for mixing and pumping fluids in microfluidic devices. The particles act as tiny stirrers. Dynamic colloidal crystals can be used to create self-healing materials and smart fluids that respond to magnetic fields. Magnetic particles can be steered through the body, and their spinning can help break up clots or deliver drugs to specific locations. The ordered structures can be used to create photonic crystals with tunable optical properties controlled by magnetic fields. Let me ask one final question. Can we extend this to 3 dimensions and create 3D dynamic colloidal crystals? The answer is yes. By using 3-dimensional rotating magnetic fields, researchers have created 3D dynamic colloidal crystals. The physics becomes even richer in 3 dimensions. Let me summarize the key concepts we've covered. First, the Reynolds number determines whether inertia or viscosity dominates. For microparticles, we're always in the low Reynolds regime, where viscosity dominates. Second, the spinning frequency and fluid viscosity control the strength of hydrodynamic interactions between particles. Third, dynamic colloidal crystals form when magnetic attractions balance hydrodynamic repulsions from spinning. Fourth, crystal formation and melting is completely reversible. We can tune it by changing frequency, viscosity, or concentration. Fifth, the physics changes dramatically across length scales. Thermal fluctuations matter at nanoscales, gravity matters at millimeter scales. And finally, these systems have diverse applications from microfluidic devices to targeted drug delivery.